Hello and welcome back to a video series on MAC 1140 Precalculus Algebra. My name's Sean Perry. These are guided notes number 10 in the series on section 2.5, Properties of Logarithms. This first question wants us to match the statements in this bank with the statements in this bank. Let's see if we can't do one better and just evaluate what they must be. Here, this is equivalent to the log base b of b to the 0. And as we saw from the cancellation property of logarithms in the last video, that makes this 0. Just as the quotient of two like bases is the difference of their exponents, the logarithm of a quotient will be the difference of the logarithms of the numerator and denominator respectively. This one again follows from the cancellation property. Just as a power to a power is the product of powers, the logarithm of something being raised to a power is the product of that power and the logarithm. Just as the product of two like bases gives the sum of their exponents, the log of a product is the sum of the logs of the components of that product. Understanding that b is the same thing as b to the first power, log base b of b must just be 1 by the cancellation property, in the same way that the log base b of b to the n must be n. This last one is already simplified by, I imagine, just because of exclusion, that they probably want something involving the change of base property here, but let's scan below and see what we have available to us. Ah yes, there it is. The idea here being that we can convert between log base b and log base anything else that we'd like, as long as it's a valid base, by taking the log in that base of the argument and dividing it by the log in that new base of the old base. One of the fun properties that implies that they don't mention here, which I'll just put off to the side here as a fun little note, is that if you take the log base b of a, if we use the change of base formula to instead switch to the log of a, then we wind up with log of a on top divided by the log base a of b. But the log base a of a is just 1. So we wind up with the log base a of b as a reciprocal. This is one of the few times that we could, for example, write a property of logs that has a power involved. But I digress. Keep in mind that if you ever want to test out a new property, you could always double check it on the calculator. All right, let's jump back in to these. Rather than match them with what they have above, let's just write what they must be. Here I have a product. We can bring products inside a logarithm as an exponent. Notice that this has the property of going from one level of operator, and by level here I mean that the operators are kind of ranked, right? If you have addition over and over again, that's what multiplication is, and multiplication over and over again, that's what exponentiation is. So they kind of have a tiered system here, and we go from exponentiation inside to a product outside. It's almost like the logarithm helps us step down the operation on its arguments. Here's a similar idea. If I have log base b of m times n, we step down from multiplication inside to addition outside. Same thing with the inverse of multiplication, namely division. Here we have 1. The log base b of any b will give us 1. This is the power that we must raise b to in order to get b. Likewise, if we took the log base b of any b to the n, the power that we have to raise b to get b to the n is just n. Here we have our change of base formula again. Writing this in terms of the original base b, we'd have log base b of a. Log in any base of 1 will give us 0. And reminding me what they said above, this is actually the cancellation property of inverses in this other way, composed into the exponent. Now we would like to evaluate these expressions without using a calculator and give exact answers. This will rely on the properties above. Log base 10 of 10 to the negative 8 is just minus 8 from the cancellation property. Here, I would want to see that we're dealing with the log base 10 of 10 to the 2 sevenths. It's 10 to the 2 because we're dealing with 100. Sevenths because that's the exponential version of this 7-indexed radical. This tells us that the answer will be 2 sevenths. Again, we're dealing with log base e here, and so this will just wind up giving us a minus 6 back. This one is e to the 7/3, and so taking its logarithm, we just get 7/3. These next ones are also just applications of the cancellation property. If we compose an exponent with its logarithm, that is to say, if we compose an exponent of a certain base with the logarithm of that base, we're going to wind up with the argument because the exponent and the logarithm are inverses. Using the product property means rewriting this as the ln of m plus the ln of y. When we see a product inside, we write it as a sum outside. This can be applied over and over again to each term in a product. There's no difference when dealing with numbers between adjacency, meaning multiplication, and the dot, meaning multiplication. So this is just going to be log of q plus the log of v as such. Here we're using the quotient property in a similar fashion. We take the logarithm of the numerator and we subtract the logarithm of the denominator. Here we have one that has a little bit of a twist to it. There's actually two numbers in the denominator. Notice that if we take that in two steps, we're going to need to subtract not just one of them, but both of them. But we need not do this every time. We need just remember that if there's a term appearing in the denominator, then it will be subtracted as such. The power property says that we bring out each exponent as a product with the logarithm, leaving its base within. Similarly, this would bring out an x here and leave g inside of the logarithm. And this is even true if there is a function in the exponent. We just bring that function out and rewrite this term within. Now, I can't help but notice, but this one could be simplified, so let's have some fun with that. In fact, there's a couple things we could do. We could note that since 4 is 16 to the 1/2 power, that this is just 1/2 times y plus 2. We could have also distributed the logarithm here before evaluating as such, but also we could have approached this in a different way. We could have said that log base 16 of 4 to the y plus 2 is equal to log base 16 of 4 to the y times 4 to the 2, splitting this up by the properties of exponents. And then the properties of logarithms would tell us this is log base 16 of 4 to the y plus log base 16 of 4 to the 2. Well, 4 to the 2 is just 16, so this would just give us 1. Pulling a y out and recalling that the log base 16 of 4 was 1/2, we could also get the same answer. I just wanted to note briefly that one could consider the power rule and the product rule to be fundamental in the sense that the quotient rule could be rewritten as a log of a product. This is m times n to the minus first power. But then this would give us log of m plus log of n to the minus 1, which is of course log of m minus log of n by the power rule. And so we see that there is a great harmony between the properties, as there must be for consistency. Here we're asked to find an exact value of an expression given the exact value of certain components of that expression. Notice that if we rewrite things using properties of logs, we could pull apart the product as a sum, and we could pull apart these powers as products, with the log of a and the log of b being here multiplied by 2 and 3 respectively. Substituting in our given values, this now boils down to arithmetic as such. Here we're asked to expand a logarithm using the appropriate rules. Anytime we see a product, it's going to become a sum, and anytime we see a power, it's going to become a product. So we will then have the natural log of 19 plus 8 times the natural log of y plus 7 times the natural log of b. In similar fashion, here I have a product and a couple different exponents to worry about. We could distribute the exponents, or we could simply start by taking the first exponent and bringing it outside. Now splitting up the middle part, we get addition, where there was a product before, and a product with 2, where before we had a square. If we distribute our 4, we get the following, and let's note that that's what we would have gotten in the first place if we had first distributed the power of 4 using exponent properties to get b to the 4, x to the 2 times 4, or 8. Then we could have proceeded to this directly. Either way is fine. Here we're being asked to do something similar. We can take this in steps, but once you get used to these problems, you'll often be able to just write down what the expansion is. Let's keep in mind that the second root is the 1/2 power, and as such, we could pull out a 1/2 to begin. Leaving this 1/2 out, we could pull this apart with subtraction, and this b to the 5th will pull a 5 out. Notice as before, it's still subtraction because this term was in the denominator itself. So we still get a negative here. In the same fashion, I'm going to do this one in one step. We have a log of y. We are multiplying that by this term, so we should pull out a 1/5 log of 100 minus log of 10 minus 1/3 the log of w. Now I can't help but notice we have common logs of 10 and 100. This is 10 to the 2, so this term will be 2/5 minus the log of 10, that's 10 to the first, and combining these, we'll get log of y plus 1/3 log of w, and bringing our constants to the end, that'll be minus 3/5. Here we're being asked to find an exact value for this expression, and we note that 6 is not a power of 3, neither is 2. And so we're probably going to write this in terms of log base 3 of 2. We need not carry it any further if we are looking for an exact value. That is to say, log base 3 of 6 is the log base 3 of 3 times 2, which is log base 3 of 3 plus the log base 3 of 2. The log base 3 of 3 can be simplified. That's just 1. The log base 3 of 2, however, cannot be simplified. To help us analyze the second term, it might help us to know that 1152 is 7 2's and 2 3's, because then the log base 3 of 1152 is the log of that product, which is equal to 7 log base 3's of 2 plus 2 log base 3's of 3, which is just 1. Since this third term can't be simplified, let's proceed now to the answer. How do I simplify log base 3 of 6 plus log base 3 of 1152 minus 8 log base 3, 2. As we saw, this first one becomes 1 plus log base 3 of 2. This second one is going to become 7 log base 3's of 2 plus 2. And finally, we are going to subtract 8 log base 3 of 2. Can't help but notice we have 8 log base 3's of 2 here minus another 8 of them. Those all cancel, and we just get 1 plus 2, which is 3. Here we want to work in a different order. We want to combine these logarithms. Again, after you get kind of used to the pattern, you'll be able to do this in one step. But for right now, I'll show a little bit too much work, bringing first the powers inside from the products outside, and combining this subtractive term by making the argument a quotient as such. Here we're asked to bring this in and write this as a single logarithm and not to use fractional or negative exponents. That's fine. Negative exponents are just reciprocals anyway, and fractional exponents, apparently, they prefer the root notation. It's the same thing. So let's write this as log base 6 of x to the 5th minus log base 6 of the square root of y plus log base 6 of z to the 4th. Any term that is being summed that is positive is going to result in a product in the numerator of this fraction we're going to construct, and anything which has a negative is going to be in the denominator. So we wind up with the following expression. In the same way that because exponential functions are one-to-one, if we know that two exponential functions are equal to each other, this implies that they must have like arguments. The reverse direction is trivial. Of course, if f and g are equal, then raising them both into the power of e, or any base, would make them equal still. That's just the substitution axiom. But the forward direction is non-trivial, right? In general, if things are not one-to-one, like how the square function is not one-to-one, knowing that x squared was equal to 4 and z squared was equal to 4, this wouldn't tell me that x was equal to z, because it could be the case that x was 2 and z was minus 2. Right. So, but if they are one-to-one functions, as the exponent is, and as its inverse is, the logarithm is also one-to-one. So we have that log base b of any function, constant or otherwise, equal to the log base b of any other function, is going to tell us that the two functions are equal. Again, the other direction is trivial. The forward direction is an interesting consequence of the fact that logarithm as a graph is indeed one-to-one. If you draw any horizontal line, it will only hit your curve in one place. Recall, one-to-one functions pass the horizontal line test, and such functions have this property. Here we have some discussion of the change of base formula. Most standard calculators do not have the ability to switch out bases in this way, although perhaps that's not true anymore. Modern calculators have the ability to change out bases directly, but some older calculators do not. The only buttons on an older calculator might be the ln of x and the log of x, the base 10 for the common log and base e for the natural log, logarithms. So how might we rewrite things on a calculator? We could use the change of base formula. This is true for any choice of base a, and as such, it's true for natural log. You could take the natural log of an argument divided by natural log of the base, or you could take the common log. Both of these quotients would give you the answer for this particular evaluation. So for example, here, if I wanted log base 2 of 66 to give me some decimal place approximation, I could take ln of 66 and divide it by the ln of 2, as such, using the ln button here on the home screen. Now that being said, your TI-84s and above will often have under the math icon a log base, which will allow me to put the base and argument where I want them. So a more modern calculator might be able to evaluate this expression, but regular scientific calculators will in general not have this functionality, and you'll have to use the change of base formula. So here we got 6.044 and so on, which is approximately equal to 6.04. In the same fashion, I could take the common log of 50 and divide it by the common log of 9, which would give me the following decimal, or I could go and get a log base command, fill out my base and argument appropriately, and get the number this way if you're using a TI graphing calculator or the like. That gives us 1.780 and so on, which is approximately 1.78. Here, we're asked to find the exact value of this expression, but recall that we learned at the beginning here there was a way to be a little bit crafty when it came to applying the change of base formula in terms of switching the roles of base and argument. Let's see if we can't apply that thought process here as well. First, let's recognize that 125 is 5 to the third power, because that's going to let us see the 5 here. If we pull out our 3, I'm going to bring it all the way up front. Then we have log base 5 of 13 is equal to the log base 13 of 5. And which either one we like, we could switch the base around. Let's take this second one and apply the change of base formula. That would give us log base 5 of 5 divided by the log base 5 of 13. But as we saw in the property, that's just 1, and these cancel to 1, and so we wind up with 3, and that's the end. That's it for this video. Thank you very much for your patience, and have a great day. Good luck with your studies. I'll see you in the next one.